Good afternoon. Okay, so we know now. We know now when we want to determine the heat of a reaction or the enthalpy of a reaction, the change in enthalpy of the reaction, we take the enthalpies of formation of our reactants. Don't forget the stoichiometric factors. Take the sum of those, and you can look those up. These are in books, in tables, in the back of your book or in the web to make sure that you get the right number. And you take the enthalpy of formation of the products, and you subtract the sum of the enthalpy of formation of the reactants. The difference, if it's negative, will be an exothermic reaction. That means there will be heat given off. If it's positive, you have to put heat into that reaction in order for it to go. Now you have. Of course, we know that we have to measure, or you have to have these enthalpies of formation tabulated. So there is not every reaction that is possible, or every compound that can be formed is not tabulated. For example, biomolecules, they are large molecules, and nobody really is interested in measuring the enthalpy of formation of a huge protein, okay? Because that protein might change a tiny little bit, and then you have to measure it again, and then it have another change, you measure it again. And so this is not a very economical way to measuring all the enthalpies of formation of organic molecules, especially biomolecules. So what the biochemists do, or the microbiologists, or the molecular chemists, what they do, they have this huge molecule, and this is the reactant, and then they have the same huge molecule, this is the product, but there are only a couple of reactive centers changed there. So there were a couple of groups reformed. And so with this, they would like to know, is this an exothermic or an endothermic reaction? And what they do is, they say, okay, why don't I break all these bonds? I know what the bond energy between a C single bond, C double bond, C triple bond, or a Cl bond is. So I break these bonds. Breaking bonds, as you all know, if you take nothing home from this lecture, you will take home that breaking bonds, you need energy. And so with this, you have to put in energy in the system. And now you have these couple of bonds, you have them broken, and these couple of atoms, or these groups, they are atomized now, okay? And now you have them in the gaseous state, or you have them dissociated. You dissociated these bonds. Now you're taking them and reformulate now these new bonds that you need, these changes of bonds that you have. And with this now, when you form bonds, you know that you get energy back, okay? Energy is released. So when you break these bonds, you have the energy that you need to put in the system minus the energy that you get out when you form these bonds. If this is negative, then it is an exothermic reaction. If it's positive, it's an endothermic reaction, okay? So with this, these wizards of biology, or microbiology and biochemistry, they can say, okay, I break these couple of bonds, I break these couple of bonds, and we make these bonds in a different way. I have an exothermic or an endothermic reaction. This is why we talked about bond energy, and you need to remember that if you have carbon-hydrogen bonds, that they depend on the environment. This is also an approximation only, okay? It's not down to the last decimal. It's an approximation of these bond energies. For example, if you have a carbon-carbon single bond, it's the average of many different carbon-carbon single bonds, depends on the environment here, what kind of other groups you have, is 348 kilojoules per mole, and the same is true for double bonds and triple bonds. Nevertheless, there's only one kind of hydrogen bond, one kind of chlorine bond, this is not an approximation, or one kind of HCl bond, this is not an approximation, or one kind of nitrogen bond. Okay, so now we have seen that we are changing energy in a reaction, and we have seen when we start a reaction, and this has the reactants have together this kind of enthalpy of formation, and then we have the products, they have together these kind of enthalpies of formation. The difference, obviously, is the enthalpy of reaction. And so as I'm pointing this here, this would be a rolling down enthalpy hill. This would be going from a higher enthalpy state to a lower enthalpy state. So there would be a release of energy, a release of heat in this case. But you could also have this case where it would have to roll an up enthalpy hill. And so far, you probably have this idea and the inkling, if it has to roll up enthalpy hill, then this reaction will not happen. This is sort of what we understand at the moment. If it goes down enthalpy hill, then okay, then it's exothermic, then it works. If it's endothermic, I have to really push it. I have to put heat in there in order to get it up enthalpy hill. And actually, there are reactions, many reactions, that are endothermic, but they roll up enthalpy hill because you put it in, but they are spontaneous. What does it mean? Spontaneous is a reaction that happens by itself, okay? And so, obviously, there are reactions where there is heat in here, but then it happens by itself. So this is something very, very strange to you because we haven't learned about the completeness of thermodynamics yet. We just have talked about the exchange of heat, enthalpy of reaction and enthalpies of formation. So what we're going to talk about is what really drives these chemical reactions. What is the driving force? So if you, for example, remember we had this bromine gas standing over there, and I had this long tube, and it was evacuated, and I was racing it. Of course, it was much faster than 20 meters per second or something. No, 5 meters per second. And so I never could win. But the question you have to ask yourself, why on earth does it go back into that container here? Why does it stay distributed like this? So you have wood at home, you burn wood or coal, so it makes CO2 and water. If you take CO2 and water and put it together, you never get wood back. Okay? Or your car, the iron in your car takes the oxygen out of the air and it slowly rusts. But then you have a rusty car. But unfortunately, the rusty car doesn't become new again. Why is that? Okay? So that's the direction of change. And what drives the direction of change? So obviously, it's not that energy alone, that heat that is liberated. It must be something else. And we talk about this today. You have to ask yourself, why does a ball not roll uphill? Why does it only roll downhill? That's the same. It's a driving force behind it. And this driving force, as you probably know, is the entropy. And this is for spontaneous processes. And we talk about this today. This is a very difficult concept. So I will have the fullest understanding if you say, oh, okay. But at the end, you will get that concept. Some of you, but most of you will get that concept. Okay? So let's do an experiment. If I have 2 volunteers, please. 2 volunteers, the 2 of you, please. Yes? Nothing bad's going to happen. That's what he always says, actually. Please. Okay, there's your safety glasses. It's not a beauty contest. And so far, look very professorial with those. And so if you could stand next to each other, please. No, look at the audience. They're the beautiful people, okay? So I give you this one here, and I give you this one. We open this. So these are 2 solids, okay? In this solid state, obviously, they like to be solids because nothing is happening. They are solids. They like that. But when I put water over this, on this, please don't spill it on your legs here. Maybe I should have gotten somebody with long pants. So if I pour water in this here, and so you're going to be my temperature sensors. You say, does it get hot or cold? All right? So this here, and this here, and so the moment you feel something, you let me know what's happening. It's getting warm? It's getting cold. It's getting cold. So this is exothermic, and this one pulls energy out of the surrounding because that's why it's cold. So we have seen that this is what we have here, that the enthalpy itself is obviously not enough. I don't put any energy in there. This gets cold, and this gets hot. Is it very warm? Yes. It's very warm, yeah? It gets up to 60 degrees. It gets very hot, actually. Hang on to it. Okay. I'm just kidding, okay? And this one, does this get cold? Gets to freezing, actually, all right? So this is, we have both an enthalpy of reaction, and the one is positive, and the other one is negative, all right? So if this gets hot, that releases, and this one sucks in energy from the surrounding. That's why it feels cold. All right, thank you very much. Good. Is it cold? Yeah, it's cold, huh? Want to feel it? You agree with me? It is the hot one. Good, okay. So now let's talk a little bit more about this. Let's think about gases. Now, if I have a gas here in a closed space, there's a volume and there's a pressure in it, it moves around with its, depending on its temperature, and this is equals the energy then, okay? So if I all give them numbers, okay, and each of them has at a certain point in time a different kinetic energy and a different position, okay? So now if I look at this is a snapshot. This is in relation to all these. So this would be a whole number of different states. I combine this one here with those states. That would be, let's say, one microstate. One combination. So now this is moving. This is a gas. Remember, we had these little steel bearings which we were moving around on the shaker table. There were the large ones and the small ones. And so if you would have followed one, and then in respect to the other ones, you take a shot in time, freeze it, and then you have all the other ones have a certain velocity and a certain location and a certain direction. But the moment you let it go and stop again, they all will have a different velocity and a different direction. So that's every time if you look at one in relation to the other, that's a microstate. So every snapshot, I look, new microstate, okay? They're moving around, okay? So they have an incredible large number of different statistical distribution it can have. If you look at one and then put them in relation to the other. But the others also have numbers. They are individual atoms, and so they can have a humongous number of different states, different microstates. So this is what microstate is this statistical distribution of arrangements. You know, you could have this one here, and the others are like this. Okay, now you have this one here, and the others move all around. Or one moves around, okay? So if you would open this up here, for example, you put one in here, and then you combine this with this over there, that would be one microstate. Then you have two in here, and you combine this with the 1 mole minus 2. So you have another number of microstates. And this was only if you look at 2. And then you have 3 and 4 and 5, and you have a whole mole. You have a large number of statistically distributed situations, states, okay? So when I open this up now here, and I have a vacuum, what happens? If I call this one microstate, of course we know there's many more than one microstate, but this one picture would be one microstate if I just look at this here, okay? That would be determining the whole picture. It would be one microstate. How many microstates would I have here now? 2, exactly. So I doubled the volume, I expanded against the vacuum, so there's no work done, no heat exchanged, but I have a change in the microstate. So that means if I have this here, and I say, why don't you guys get all back here to the left? You think there's a high likelihood at all that this happens? That you have nothing in here and this is open and all of them are in the left? No, because this is highly improbable. It's highly improbable that you have, there is some probability, but the probability is infinitesimally small, okay? So that means a spontaneous process, if they go by themselves, spontaneous, the reverse never occurs. So this would be a spontaneous process. You have the expansion here, and it would be impossible that it goes back by itself without you doing something to it, or to the system, that it would look like this again, all right? So the reverse never occurs. This is a spontaneous process. Time, of course, we don't care about time, because we are talking about initial state and final state. When you have, for example, the aging of magnesium and oxygen, I just see magnesium and oxygen, if they react with each other, they are sort of magnesium and oxygen, and then they get in a more and more stable state. They age. In geological times, they age. So they form minerals. And they have much less microstates than if you have just magnesium and oxygen, which is pretty unordered. But then when it crystallizes, it becomes more and more ordered and more microstate. It has less microstates. So that means if we equilibrate the pressure here, there is no exchange in energy, okay? That cannot be work, but there is not any heat exchange either, because that's the condition we have. So what is that thing here? Why is that happening? Because we have a new state function. And the state function is called the entropy. It describes the order of a system. Now let me see. The entropy of your dorm room, okay? The entropy of your dorm room, when you start in the semester, you're all fresh, you're rested, at least some of you. You're rested. So have the few books you have there, and the computer software is there. There are even no books anymore. But anyhow, to have everything is relatively orderly, and then all hell breaks loose. There comes midterm 1 and this one, and midterm 1 and this, and so you start even using paper again, and you're writing on paper, and it's all over the floor, and there's pizza over there, and there's some food. Oh wait, it's moldy even, you know. And so the entropy, the order of the number of microstates in your room has tremendously increased. Okay, tremendously. So there's a steady increase, not so steady actually. There's an increase in entropy in your room. So that means entropy is a measure for the order of a system, and your room has increased in entropy. So what happens in the Earth is the universe, that the entropy of the universe is constantly increasing. So you look at the entropy of, and you remember we have the system, that's the little thing we're working with, and then everything around is the surrounding or the universe, okay? So the entropy of the universe is always increasing. That means at the very end, and we won't be around to witness that, fortunately, and we will only see relatively small entropy changes of the universe, but at the very end, when the entropy is completely disordered, the amount of energy is still there, because we don't lose energy. The universe doesn't lose energy. You don't gain energy, and you don't lose energy. But now, there's no more order, so you can't make these molecules work. To go from an ordered system into a disordered system, they all have energy, but you can't extract any useful work anymore. And with this, the universe is at its highest state of disorder. So the entropy, that was this guy, Boltzmann, he was a pretty arrogant guy. Actually, he came, I don't have time, but nevertheless, he was in the early 1900s, he was a guest of the Hearst, the publishing people Hearst, and the Hearst Castle, you know, and he was invited to give a series of lectures, and then he was invited at the house of the Hearst, and he was when he went back, actually, he was very, I would say, non-complimentary towards his host, you know. He was saying something about their cooking and so on, and so on. And they gave him lots of money to come there and so on. He was not a very grateful and thankful person, obviously. But also, he was highly depressed. And when he came back from California, he had to go back to Vienna. He committed suicide. Okay, so this is maybe has nothing to do with the change of climate, but on the other hand, this is what happened to Boltzmann. And so if you go to Vienna at the cemetery there, you see on his grave is S is K times ln omega, and this is the W, means that's the probability of a system. Okay, the entropy of a system is KB, is the Boltzmann constant. Remember, that was the R divided by NA. That's the Boltzmann constant. That's a fixed constant. Times the natural logarithm of the distribution of microstates. Okay, that is the W is for Wahrscheinlichkeit in German. It means probability. So so delta S is larger than 0. That means in this case, for example, the change in entropy was a positive change. So there was no heat exchange, there was no work done, but the entropy of the system changed and it increased. Okay. Now, so if you, for example, have a hot body, no, never mind. If you have a hot piece of metal, okay, you have a hot piece of metal and you put this in a cool bucket of water. The heat always goes from hot to cool. It never goes from cool to hot, okay? So that some heat gets transferred from a cooler system to make a hotter system even hotter. Doesn't happen, all right? That's also part of the entropy. So now they come into equilibrium, and so with this you have the change in entropy, and this is a statistical thermodynamic explanation, and this is an explanation of the entropy. The change in entropy is the change of reversible heat that you can reversibly exchange at a certain temperature, and you will get the hang of this as I go on in this lecture and in the next lecture. So now let's do a little bit of statistics. We have 6 distinguishable objects. These are 6 billiard balls or whatever. They have 1, 2, 3, 4, 5, 6. How many ways can you have 4 in the left box? So you can have 1, 2, 3, 4 in the left box, 5 and 6 would be in the right. You can have 1, 3, 4, 5, and 2 and 6 would be in the right box, and so on. Why don't you try to intuitively figure out how many ways can you have 4 of these billiard balls in the left box and 2 in the right box? Is it A6, B15, or C32? Think about this. You can actually count it through, but you also can use statistics. Some of you, who know statistics? Okay, everyone. Okay, good. Thank you so much. You saved my day. These are just 6 atoms that you want to arrange into microstates, okay? How many microstates can you have? Discussion already? Okay. Yes, I know. Just thinking. Takes a long time for me. Okay. So there's 260 people say 59% say it's 15. How did you derive to that? Do you know how you derived it? Did you just count it, or is there any formula for that? Anybody heard about? Yes, sir. Combinatorial, yeah? And so there's some factorial mathematics we need to do. And you know how this goes? Excellent. So you know how the formula works. Okay, let's find this out. If you can keep your calculator handy, please. That's a TI 5 million. Is that the one? Okay. If you keep that calculator handy, because you can help me with a question then. Okay. So I go with B. All right. So what's your name, sir? Like Dylan, he went with B. He said, I have a calculator. But in order to use the calculator, you need to know the formula, actually. Or maybe it's even written in there. I don't know. But so the answer was B. So let's see why the answer is B. So if you have, and this is something just to warm you up, this is nothing I'm going to ask you in the midterm or in the final, but that you sort of understand statistical thermodynamics a little bit, how you can derive this from microstates. So this gets you warmed up a little bit how to work with microstates. So there is, in general, the number of ways to choose R things. What R things is these 4 things here. From a group of N things, that would be 6. 4 of 6. So you say, okay, N factorial. That is the whole number. That's 6 factorial divided by R factorial. This is 4 factorial. N minus R is 6 minus 4 is 2 factorial. Is that what you did, sir? Dylan, okay. So if you calculate this, that's 6 factorial, 1 times 2 times 3 times 4 times 5 times 6. That's factorial. 4 factorial, 1 times 2 times 3 times 4 times 6 minus 4 factorial. So that's 2, 1 times 2. Okay, that's 2 factorial. And this gives you 15. Now, let's just assume that we have 40 of those guys. 40, and we want to put 20 in here and 20 in here. So can you calculate this for me, please? So this is 20 factorial divided by 20 factorial times 20 factorial. Approximate. I just need the exponent. 10 to the 11 with 40 different billiard balls here, where you have one half here and the other half here, you get 10 to the 11 possibilities. 10 to the 11 possibilities. It's like playing the lottery. It's actually no, lottery is a little better actually. 10 to the 11. So this is 100 billion different arrangements here. Now imagine that you have a whole mole of this stuff. Okay, this is 10 to the 23rd. Even Dylan's calculator will not do it. It will be on spike. The number is humongous, absolutely humongous. Okay, so this gives you a little bit of an idea of factorial. Let's play a little bit more now in a minute here. We have the change of the entropy of the universe is always larger than 0. It can never be smaller than 0. Okay, because we are heading for absolute chaos. Not tonight, but in the long range, okay? We're heading for absolute chaos, all right? And so, fortunately, we don't live long enough, so our chaos will be sort of limited. Nevertheless, sometimes it feels like it's absolute chaos to begin with. So, you have to change of your system. You know, we talked about this earlier, your system and your surroundings. Remember, you had these pistons. That's the change of the entropy of your system, but the change of the entropy of the surroundings has to be larger than 0 for a spontaneous process, okay? So, you can't get it back into the genie, into the bottle, okay? And this is for an irreversible process. So, for example, this here is essentially an irreversible process. So, if you look at this likes to be in the liquid